Hello, everybody. Hope you guys enjoyed that. Welcome to this week's recitation. I may be having too much fun with these opening things. Let's see. Hopefully, you guys enjoyed the great music from Ori and the Will of the Wisps in the beginning. I haven't actually listened to the soundtrack of that game. I know the soundtrack of the original Ori and the Blind Forest is very good, so decided to take a look at some of the ones you guys suggested. So thank you for your wonderful suggestions. With that said, let's go ahead and hop right into this week's stuff. Your normal early beginning of recitation announcements. You do have a homework that you're working on right now. It's the AVL homework. Hopefully you should be mostly good to get started on that after this recitation. It shouldn't be that bad of a homework if you did well on homework 4, but if you were a little bit lazy on homework 4, or if you did stuff using look ahead instead of pointer reinforcement, then it might be a little rough for you, so I definitely recommend getting started early. Homework 8 is going to be your next homework. That is the first algorithms homework in this class, so everything up to this point has been data structures, but this is the sorting homework, so it's algorithms. That's going to release on that Friday before homework 7 is due, the 16th. That's also going to be a 2-week homework due on the 30th. Now, both of the other 2-week homeworks you've had in this class have been because they went over exam periods. The reason that this one is a 2-week homework isn't because it goes over an exam period, it's just because it's a really long homework, because there's a bunch of sorting algorithms you need to code, and it just takes us enough time to actually teach all of those that it wouldn't really be fair to just give you a week, because we would have to rush through teaching and it would end really badly. I recommend this one as we kind of cover the sorting algorithms, as you kind of encounter them in the module videos, or as we teach them in lecture. Go ahead and look at the homework and see which ones you can do. Don't try to do it last minute. Again, it's not really because it's a hard homework. It's just a long homework, and doing it last minute is just going to be a lot of work. Other big thing, exam 2 is going to happen next week on the 14th. That's the same 6 a.m. to midnight window to take the exam. Make sure that you're starting the exam before like 10:45 so that you actually get to take the full time. Hopefully we don't get things like power outages happening during this exam. Hopefully we don't have some of the issues we had during exam 1. We're going to do everything we can to prevent that, but we'll see. Practice exam answers are going to release on the Sunday before the exam at noon. This time I've scheduled them to get published under the file section, so I can't forget this time. But those will be there, so definitely if you haven't looked at the practice exam yet, probably helpful to do that. Those answers will get posted on Sunday. The topic list, I guess you can ignore this. Topic list, I just posted a little bit before this recitation. Take a look at that. It's pretty much what you'd expect to be on exam 2. So all the stuff we've covered up to this point, including AVLs and 2-4 trees, but not including sorting, which will probably get covered in lecture on the Monday before the exam. As per usual, your recitation worksheet is available on Canvas. Stuff we're going to be covering today, we're going to finish up the last bit of SkipList that we didn't get to last week. That's going to be SkipList removal and efficiencies. And then we're going to talk a decent amount about AVLs today. Overall, in terms of like pieces of paper I have to use for this week's recitation, it's a lot less than I've had in the past couple of weeks. So maybe that will give me some more time to cover things in a little more detail, or maybe we'll just get through stuff faster. Regardless, let's go ahead and jump right into it. First thing today is going to be SkipList removal. So, last week we talked about how you search for things in a skip list, and we talked about how you add things to a skip list, but we never quite talked about how you actually remove things. Now, the nice thing about skip lists is removal from a skip list is actually much easier than adding things to a skip list. Also, for anyone redrawing this out, I believe it is the same skip list we would have ended on last week, so if you've got that and want to keep working on it, feel free. But skip list removal is nice that it's actually a lot easier to remove from a skip list than add to a skip list. And this kind of goes doubly with the fact that we don't actually code skip lists in this class. We just talk about them from a diagramming perspective. So if you just think about removing as just get rid of something and have the diagram fill in around it, it's actually really easy to do it that way. But even from like a coding perspective or an algorithms perspective, it's still very easy. All we need to do to remove stuff is we traverse in order to find the data. Remember, we're always going to find data on the highest level it appears, assuming it does exist within our skip list. Then we're going to remove that node, just like a regular doubly linked list. So I should specify we're removing that node from that level. And that's just a normal doubly linked list removed. That whole previous.next equals current.next, and next.previous equals current.previous. So really simple doubly linked list remove. Then we drop down to the level below us, and we remove the node from that level, and we keep repeating this until we get to the bottom level of the list. So all these removes are relatively simple to do from either a diagramming perspective or a coding perspective. Now let's just take a look at some example. If we were going to remove 35, so we start at our negative infinity in the top left. We look forward by 1. 60 is bigger than 35, so we drop down. 30 is smaller than 35, so we're going to hop over, skipping all of these to get to 30. 50 is bigger than 35, so we drop down. 35 is not bigger than 35, it's our target data, so we move to it. Then now we've reached the target, so we're going to remove it from this level by making essentially this 30 connect to this 50. So this removes this 35, then we drop down, and we're going to remove it from this level, so that's making this 30 connect to this 45. So now we can pretend that this 35 isn't in our skip list, and that 30 just connects to this 50, and this 30 just connects to this 45. So these removals are overall very simple to do. Now if I was going to remove like 25 from this also, we start, 60 is bigger, so we drop down. 30 is bigger, so we drop down. 20 is smaller, so we jump to it. 30 is bigger, so we drop down. 25 is our target, so we move over. And then to remove it, we just kind of connect the pointers around like this. So 25 gets garbage collected from this. A bit of a note, I did cross out 35 here as soon as I connected these pointers around. Technically, it wouldn't be garbage collected yet, because you could reach it by going down and back up, but kind of symbolically, that's when we removed it from the skip list, even if it didn't technically get garbage collected until we removed all of the 35s. Just a note. So that's skip list removal. Very simple to do. From a diagramming perspective, you shouldn't really even need to think about this process. You can probably just kind of take the piece of data out, but you should know in case we ask like, oh, what nodes do you traverse through in this point? Or something like that. Give you guys a couple more seconds in case people were like rewriting this whole skip list, because that can take a while. And then we're going to talk a little bit about skip list efficiencies. All right. Let's look at efficiencies. Now, before I talk about specifically skip list efficiencies, I want to talk about something that's kind of applicable to a bunch of different efficiencies in this class. And that's that when we talk about like best, average, worst, the really important question is not necessarily like what is the best, average, worst case of this. Very often it's why are these the best, average, worst situations. So that's the real question. Alternatively, you could also ask like how are the efficiencies, but if the efficiencies answer that back to you, you should probably get more sleep. But the why is the important thing here. For reference, when we talked about BSTs, why we had this worst case efficiency was because we had degenerate trees. When we had hash maps. When we had hash maps, the reason for why we had this worst case is if we have some really bad hash function. With skip lists, what's going to determine why we have these worst case efficiencies are going to be when our coin flips are really bad. Remember, skip lists were these probabilistic data structures where we flipped a coin a bunch of times every time we were trying to add things. So how good these coin flips are going to determine when we have good efficiencies and when we have bad efficiencies. An example of something that might be bad is if all of the data only ends up on the bottom level. So instead of having like a really cool skip list, we just have an ordered doubly linked list. Or if we have the data repeating on all levels, so that might be something like this, which I always love to call the skip brick, because it's just this giant brick of nodes. The top line here says determined by how good the coin flips are, with good in quotations. So how good the coin flips are is what's going to determine whether we have a lot of efficiencies. If we have this sorted doubly linked list, or this skip brick, or some really nice structure like we've seen in some of the examples. Another important thing we have to talk about with efficiencies is space. So with skip lists, no longer are we just having like every single piece of data is only one node. With skip lists, some of these pieces of data take up multiple nodes. If you remember from our previous example, you see that like 60 is in this skip list 4 times. So how much space we're actually using, and if we're using like a significant amount of more space with this data structure, that's an important thing to know. Well, let's look at, first of all, our best and average case. So for adding and removing and searching too, I didn't write it on here, but searching is the same for both of these operations. We have to think about if we have our nicely divided lists, so maybe we have like something that looks like this. So you can imagine something like this that looks pretty nice. When we when we jump to things in our top level, we're roughly dividing our list in half. Because if you remember, every time we go up or down a level, that corresponds to either doubling or halving our current data. We expect roughly half the data to be on the level above the bottom, then half above that. So where these nodes on our top level are can kind of roughly split our list in half if we have good luck. So when we do these add and remove operations, our ability to skip over all of these spots of data is going to be just like when we make decisions to go left or right in a BST. So this is where we get this log n efficiency from, because we are able to skip over a lot of our data on average, or in the best case. Now space. I claim for some reason that we're only taking up O of n space, which is like the normal amount you would expect for any data structure. Now the reason for that is exactly what I said earlier. On the average case, we've got n data on our bottom level, then n over 2 data on the level above that, then n over 4. And if you remember that, that's a really simple converging series that you probably learned in like calculus and other stuff. That just sums up to 2n, which in big O notation, we can just drop that 2, and it's O of n. So that's really nice. Even on average, skip lists don't actually use a asymptotically significant amount of data extra compared to like a BST or an AVL. Now, in the worst case, that's a completely different story. If we think about our data just all being on one level or all being on every single level, then adding and removing are both really bad, because this is just adding a piece of data to a sorted doubly linked list, and we just need to traverse through that entire list to find where it's supposed to go. Similarly with removing, we need to search for the data in a sorted linked list, which we're not even able to use fancy techniques to search in a sorted linked list. We just kind of need to go node by node by node. So both of those are O of n in the worst case. Now space, I kind of have to put an asterisk on here, and this asterisk does not mean amortization. I realized after I wrote it, I probably should have used a different symbol. But the really like trivial case is you say, okay, if I've got some broken coin that literally only ever flips heads, then I use an infinite amount of space because my nodes go on who knows how many levels. But we always like to say when we make our skip list to usually cap the number of levels we're allowed to have at roughly log n. This prevents our efficiency. This prevents our memory from getting too bad by having to add like 5 new levels just from some really unlucky coin flips. And this also mitigates our space complexity. So by capping our levels at roughly log n, our worst case space is clearly when every piece of data is on all log n levels, where we have this O of n log n space complexity. We would always specify on an exam for these like worst case things. We're saying like, okay, cap your space at cap your levels at log n, because otherwise you kind of get trivial examples. I'll give people a little bit to ask some questions about SkipList before we move off of them. Also just to write everything down if they haven't managed to get all that already. But then we're going to jump on to AVLs, which is the big topic of today. Alright, it's not looking like we really have any questions yet, so I think I'm just going to go ahead and keep moving forward. Overall, skip lists kind of look a little scary because they've got all these random stuff, but really they're not actually that bad. AVLs, this is our next thing. Like BST stood for binary search tree, AVL stands for Adelson, Velsky, and Landis, as one does. But those are obviously the people that came up with this idea, and what AVLs are they are these self-balancing versions of BSTs. So when I say BSTs, I mean like in kind of the category of trees. Remember, we have trees, then binary trees, then BSTs, then AVLs are a subcategory. So every AVL is a BST, but not every BST is an AVL. Now, the reason we want to include this self-balancing property is because you might remember that BSTs had this really bad degenerate linked list case where we would have all these O of n efficiencies. So we're going to make it so that our tree is always balanced so that that degenerate case is never possible. Now, how we're going to accomplish that is every time we make any operation that changes our tree, note these operations are add and remove, those are the only ones we really have, clear is kind of trivial. But every time we do an add or remove operation, we're going to make sure that the tree is balanced. How we do that is through stuff we're going to talk about on the next page, but we're going to ensure this balance after every single time we change the tree. Now, we do have to slightly alter the actual structure of our tree in order to make this work in an efficient way. Previously, you'll remember in BSTs that our nodes all stored 3 things, a left and right child and a piece of data. Now in AVLs, we're going to change that so nodes are storing 5 things instead. The same 3 things as the BST, and now these 2 new things. The first of those is going to be height. This is the exact same height we talked about when we talked about BSTs. We're just, instead of having it be some quality of the tree that we calculate in O of n time, now it's going to be a variable that every node remembers about itself. Remember that our definition of height is that we take the max of the left child height and the right child height and then add 1. In BSTs, this was a recursive calculation. You recursively called a method on your 2 children, and that's how you determined it. But in AVLs, this is no longer a recursive definition, because these are no longer recursive methods, these are now variables. This can be like node.left.height and node.right.height. So we can calculate our height for any given node really quickly, just by looking at our 2 children. And once that height value is calculated, we can just get it in O of 1 times by looking at our node's variable. So our height of the whole tree, instead of doing some crazy calculation, it's just going to be root.height, something really simple like that. Now, with this height variable, we can do some useful stuff like store another variable called balance factor. Now, this balance factor is going to help us determine whether or not our tree, or any specific node within our tree, is currently balanced. How we calculate it is we say a node's balance factor is the height of the left child of the node minus the height of the right child of the node. Note we're calculating balance factor by using our children's heights. Some people use balance factors here. It's heights that you're subtracting. Now, what we're going to require is that every single node has to have a balance factor between -1 and 1. So that's 3 possible values, -1, 0, or 1. You'll note that when we talked about like all the different shape properties of trees, that this is just exactly our definition of balanced. We said that to be balanced, you can't have any two children whose height differs by more than 1, and that just is this exact definition. We're just writing it in a different way that's a lot easier to keep track of. Now, if any node breaks this after an operation, so if any operation causes our balance factor to go outside this -1 to 1 range, then we use a rotation to fix. And that's going to be the main focus of today, is talking about these rotations and how they fix our imbalanced trees to create balanced AVLs. So we'll give a couple more seconds, and then we'll talk about all the rotations. The next page is a little heavier on stuff. Alright, doesn't really seem like there's too many questions just yet. So now let's get into the real meat of today, which is talking about these rotations. Now, before I get into this, I will say, I will move the page down a little bit so you can really see what's on the bottom in a second, but the real thing you probably want to get out of this page is this table right here, which is how we determine what rotations to do. So definitely make sure you've got that down in some place where you can see it. That'll help you a lot on your homework and when you're doing like AVL examples. These are just kind of examples from this table. So, as I mentioned earlier, these rotations are how we fix imbalanced nodes. So anytime a node's balance factor is either 2 or -2, turns out one operation can't make our balance factor any worse than 2 or -2, as long as we're fixing it after every single step. But it's still generally nicer just to say greater than 1 or less than -1. But I don't believe it's possible to have a 3 or a -3 or anything worse than that, assuming that you're starting with a valid AVL and only doing one operation. Now, a little bit of interpretation. A negative balance factor, that means that our current node is right heavy, because remember we subtract the right's height, so this means that the right height is a lot greater than the left height. As opposed to that, a positive balance factor means that our node is left heavy. The left height is a lot greater than the right height. Now, something we might have when we're doing some rotation, and you'll see a couple examples of this today, is if we have like kind of a zigzag pattern. So if we have a right heavy node whose right child is left heavy, or a left heavy node whose left child is right heavy, then we kind of have this weird like zigzag that you'll see on the other examples in this page. And when we have those cases, then we need to do a double rotation. Once I get through this table, I'm going to shift my page up a bit for a second. So what this looks like is if our parent's balance factor is -2, that means that we have a critically right heavy node. We can look at the right child's balance factor. We don't care at all about the left child's balance factor. Our node might not actually have a left child because it's right heavy, but we look at the right child's balance factor. If it's opposite in sign to our parent's balance factor, note we're not counting 0 in this, so opposite in sign of -2 only means 1, then that means we're going to need to do a double rotation. So if our node is just regularly right heavy, with a child who's either slightly right heavy or balanced, then we only need to do a single left rotation. But if we have a critically right heavy node whose right child is slightly left heavy, then we need to do this right-left rotation. Now, sometimes people ask, like, okay, what if somehow the right child's balance factor was like -2 or 2 or something? Well, the nice thing is you'll see when we talk about operations that we are going to update all of our balance factors from the bottom up. So if our right child's balance factor was imbalanced as a -2 or a +2, we would have rotated around that node first, and then gone up to the parent. So it's not possible for these child balance factors to be out of balance critically. So that's a really nice thing. There's only these 3 possible values to go between. Now, exact counterpart to this, if our parent balance factor is 2, that means that we are critically left heavy. This means that assuming our left child isn't slightly right heavy, then we're going to do a right rotation. If our left child is slightly right heavy, we're going to do a left rotation, then a right rotation. So that's that left-right double rotation. So we've got all of these examples. You'll notice I've kind of labeled them out to the side, 1, 2, 3, 4 going down. That's because they correspond to these other examples I have at the bottom of the page. So all 4 of these are kind of example trees I've given that are imbalanced and in need of a rotation. You'll notice that I have these 1, 2, and 3 here written as like these big nodes, and then I have these weird like triangles with A, B, C, and D down here. Now, the 1, 2, and 3, these are the nodes that actually might get changed during these operations. In fact, in all of these operations, they get changed in some of them. Not every single node gets changed in every single operation. I'll talk more about what I mean about changed in a second. But these subtrees, these A, B, C, D, while they might move around a little bit, nothing about them ever changes. Their heights don't change, their balance factors don't change, versus in this case, when we go from this to this, it's possible that like 1 and 2 both have their heights change or their balance factors change. That's what I mean by in need of an update or in need of a change. So this first example is an example of something that is right heavy, so that's case 1. So that's something that just needs a left rotation. So you're going to go from this tree to this tree. As a correspondent, this example 3 over here is something that is left heavy. So you do a right rotation and you'll go from here to this same tree also. Now these two over here are that zigzag I talked about. You see the nodes we care about kind of go in a zigzag like this. So 3 and 1, 1 is right heavy here and 3 is left heavy here. And then, but these children, we have a right heavy node with a left heavy child and a left heavy node with a right heavy child. Now notice these nodes aren't critically out of balance, but they're still slightly heavy. So we first do a double rotation here. So I'll focus in on this example. Here we do a right-left rotation as per our table. So we do a right rotation first, and that's going to bring us to this case up here. Then we do a left rotation, and then we get to this node over here. Now to specify, the right rotation is about this node, about this 3, and the left rotation is about the root, this 1. Likewise over here, when we do a left-right rotation, the left rotation happens around this 1, and the right rotation happens around this 3. So we go from here to here to here. So all of these, through our single rotation or double rotation, all take us to this same resulting tree. Now on the next page, I'm going to walk through one specific rotation in detail, so you can see what the pseudocode looks for it looks like, and you can get an idea of how you'd implement this on this homework, or what's actually going on during these rotations. Few more seconds just for everything to catch up. There have been some questions getting asked. Thank you to all the TAs that are helping me out answer these. Now I think we're going to move on to our in detail rotation, so you guys can see what that looks like. So I'm sure you will find this helpful for your homework. So, for example, this, I should specify, this is a left rotation. So what we have here is we've updated our balance factor of like 3 down here, then we updated our height and balance factor of 2, then we get to 1, and we determine that 1 is critically right heavy. It is has a balance factor of -2, and we don't have to do a double rotation because let's say that node 2 either has a balance factor of 0 or it has a balance factor of 1. It's not that important. So first step is we're doing a left rotation around node 1. So our helper method to do this rotation gets this node passed in as a parameter. Let's just call it node. Our first step is we're going to create a variable, I'll just call it right in this case, and we're going to point it to the right child of our node. So we've got these two nodes that we care about in this rotation, node and its right child. Then the first thing we're going to do is we're going to set our node's right child to be the left child of right. So what that looks like is now this b kind of moves up here to be the child of the 1. And we actually get this really weird like M shape in our tree. This is why these intermediate steps of the rotations look a little weird. This is also why we needed to make this variable, because otherwise there would be nothing pointing to this too, and we would completely lose everything in this subtree because it would get garbage collected. So we've got to make sure to save this variable first, then do this first assignment. Then what we do to fix the rest of our tree is we set the left child of right to be equal to that node that was passed in. So you'll see that kind of takes this pointer and moves it to go to this, which is going to result in this tree right over here, which you can see that this is that balanced example we had on the previous page. Then we've got a couple other really important steps. These parentheses shouldn't be here. We want to update the node and then update the right. What do I mean by update? Well, if we look at node, which is our node 1 in this case, we can see it previously had A and 2 as its children, but now suddenly it has A and B as its children. It's possible that B and 2 had different heights. So the height of our 1 node might have changed, because we've moved things around beneath it. So we need to update the heights and balance factors of this node. Likewise, we need to update the heights and balance factors of this node, also this top node. But the order is very important. We have to update this node, and then update this node. Remember that when we look at the height and balance factor of a node, we base it off of the balance factor and height, or sorry, just the height of our 2 children. So if we don't update the children first, then when we try to update this node, it's going to be completely wrong, and we're going to get some mess that no longer works and all the balancing is going to break. So make this variable, do the 2 pointer reassignments that create the rotation, update the node passed in, update the new root of this subtree, and then we're going to return right. So this parentheses shouldn't be here. Now the reason we return right is this is because of pointer reinforcement. Remember from BSTs that we said pointer reinforcement, every operation that modifies the tree should return the new root of that subtree. So prior, the root of this little subtree was 1. So that was the node passed into this method. But now this subtree is rooted at 2. So we can imagine whatever called this method was like some set right method or like some root equals method, something like that. So when we return this new root node, that's going to get set equal to that new pointer, and that's what's going to fix our tree. This is why we stress pointer reinforcement so much, is because with pointer reinforcement, this is it for your rotation method. Without pointer reinforcement, just trying to figure out what this line becomes and how you fix it without pointer reinforcement is a complete nightmare. So please, even if you for some reason didn't do pointer reinforcement on homework 4, you want to rewrite your homework 7 code to use pointer reinforcement. Otherwise, it will be about triple the length and still fail tests. Please use pointer reinforcement for homework 7. It is practically a requirement to get your code to work. I'll give a couple more seconds, and then we'll talk about an actual operation on a AVL and see what it looks like in a little more detail. All right. So now let's look at what adding at an AVL looks like now that we're trying to keep everything nice and balanced. So the overall adding process for an AVL is going to start by adding just like we did with a normal BST. So we're going to search for some spot at the leaves to add our new piece of data, add it in, or create our new node added in. The big detail is we want to make sure we're doing this operation using pointer reinforcement. If we don't use pointer reinforcement, it's going to be really ugly to do all these rotations. And then our next step is as we unroll the recursion, which is like kind of when we're going back up the tree. Here, an important rule of thumb that people generally find helpful is that any code you write after the recursive call is going to happen while you're unrolling the recursion. So what we do during this is we update the height and balance factor, and then if our node is out of balance, we rotate. And now you'll notice what this is going to do is this is going to update every single node we passed through during the process of adding, because those are the only nodes that could have changed. If we didn't touch a node during the add process, so during the process to recurse down and add the new thing, nothing about its height or balance factor would have changed. We only need to update the nodes that we pass through. So let's take a look at an example. You'll notice I've written this AVL out here. By convention, we usually like to write the heights and balance factors of each node above it. So I've written the height to the left and the balance factor to the right. So you'll see these leaf nodes have height and balance factor 0. This node has height 1 and balance factor -1. And this node has height 2 and balance factor -1. So now let's add a new thing. Let's say we're going to add in 50. We start at this node. We're going to recurse to the with pointer reinforcement, we are going to leave this pointer kind of in the air and recurse to the right. We leave this pointer in the air and recurse to the right. We leave this pointer in the air and recurse to the right. And then we reach this null spot. This null spot, remember from pointer reinforcement, says we create a new node. 50 in it, has height and balance factor 0, as all leaves do. And then we return it, so it gets set to the right child of 40. Now we get up to 40. So before we just keep, in BSTs, we just kept returning everything all the way back up. But now we have to do our updates. So first, we update our height. We say my left child has height -1. Remember, nulls have height -1. My right child has height 0. So my new height is 1. Then I look at my balance factor. My left height is -1. My right height is 0. -1 minus 0 is -1. So now I have, this node has height 1 and balance factor -1. Then I check, am I out of balance? Well, -1 is still a valid balance factor, so I'm not out of balance. In the case that I'm not out of balance, I can just return my current node. So 30's right child gets reinforced to point to 40. So it was already pointing there, now it's pointing there again. We get to 30. We update our height and balance factor. Height is going to be the maximum of 0 and 1, which is 1. Then we add 1 to that to get a new balance factor of a new height of 2. For balance factor, a height of -1 for our null and a height of 1 for this. -1 minus 1 gives us a new balance factor of -2. Now we check, am I out of balance? In this case, yes. -2 is not a valid balance factor. We need to do a rotation. We can consult our tree. We say, or our table from earlier, we can say, I've got a balance factor of -2. I'm right heavy, so I look at my right child. It has a balance factor of -1. This means I don't have a zigzag. All I need to do is a normal left rotation. So what does this left rotation look like? Well, we can do the steps. You can also very easily visualize it. You'll see that you're going to end up with 40, 50, and 30 down here. Nothing about 50 changed, but other things about 30 and 40 might have changed. You'll notice that 30 is definitely not in the same place that it used to be. So now we look, what is the new balance factor and height of 30? Well, it's a leaf node, so it has no children. So it has height of 0 and balance factor of 0. Now we update 40. Take the max of 0 and 0, says that our new height is 1. Then our balance factor is going to be 0 minus 0, which is 0. Then we return 40. Now when we return 40 as a part of this rotation, where is it going to go? Well, it's going to go, remember what was happening is 20's right pointer was getting set to whatever this returned. And since this returned whatever this rotation returned, now what's going to happen is 20's right child gets set equal to 40. So this pointer reinforcement makes all this weird rotation logic fit in very nicely with all the operations we've talked about. So nothing over here changed. Now we recalculate our height and balance factor. The max of 1 and 1 is something... this. The max of... Did I mess something up? Remember that balance factors are height minus height. You don't use the balance factor of the children. So the balance factor of these nodes is you take the height of the left child and subtract the height of the right child. Okay, so we calculate the height for 20. The max of 0 and 1 is 1, so 20 has height 2. Then balance factor is going to be 0 minus 1, which gives us negative 1. So this is our new, and that is balanced, so we don't need to do anything. It returns it and gets reinforced as the root. So we've now done an add operation in an AVL with a rotation. Super nice. Now let's do another add operation. Well, first we're going to end up creating a situation in which we're going to have a double rotation. So the first thing I'm going to do is I'm going to add 1. And this process isn't going to result in a rotation, so I'm going to kind of go through it really fast. So all of the nodes over here aren't going to change. Except we add this 1 here. So we have to update the heights and balance factors of everything above it. So 10 now has height 1 and balance factor 1. And 20 now has height 2 and balance factor 0. So the height didn't change for 20, but the balance factor did. So nothing here required a rotation, so there's nothing else we have to do. The next thing we're going to do is we're going to add in 4. Now the first thing I'll do is I will just draw out what that looks like before we do any rotations. And then we'll do our updates and see what happens. We're going to have 20. 10, 1, 4, and then everything over here stays the same. So again, nothing that we didn't touch in the process has its heights or balance factors changed. So after we add 4, its height and balance factor are 0. We go up to 1, we update it, and we see that it'll have height 1, balance factor negative 1. We go up to 10, we see that it has height 2, balance factor of 1 minus negative 1, which is 2. And we see, okay, this node 10, this is out of balance, because I have a balance factor of positive 2. Now what's going to happen here is we see, okay, I should look at my left child, because I'm left heavy. But I see my left child has a balance factor of negative 1. This means that I've got this zigzag, and I need to do a double rotation. In this case, I need to do a left, then a right rotation. So how I do my left child, what it's going to be is it's going to say, I'm going to say 10.setLeft of a left rotate on the node 1. So what happens is we left rotate 1, and in this case that's really simply just going to give you this 4 and 1 here. Remember, this left rotation still updates our heights and balance factors. So now 1 is a leaf node, and 4 is a node right above it with height 1 and balance factor of 1. And that gets set to the left child of 10. So 10's right here now. Then we're going to return a right rotate of 10. So when we do this right rotation, now we're going to get 4, which you see 4 was this node all the way down at the bottom, but these 2 rotations are actually bringing it up to the top, with 1 over here and 10 over here. 1's height and balance factor didn't change, but when we do this right rotation, we see 4 and 10 are the two that are going to have to get updated. So 10 is now a leaf node. 4 is now height 1 balance factor 0. And then we return the new root of this subtree, which is 4. And you remember that's going to get set as 20's left child, because that's how we got down there in the first place. Again, that's that pointer reinforcement at work. So everything over here is going to be the same. Now we update our height and balance factor of 20. Height is going to be 2, because our two children have balance factor 1, and have height 1, and our balance factor is going to be 0. So now this is the result of the tree. We'll kind of draw these arrows out. We kind of went this way. This is the results of the tree after adding this 4 and doing this double rotation. So I've seen a couple of questions get asked and answered, but I will give a little bit longer for some more questions to be asked. Then we're going to look at what an example of removal looks like. Turns out it's going to be relatively similar to adding, but we'll do that, and then we'll close it off with some helpful things that will most likely help you in your homework. It doesn't look like there's too much new questions, so I'm going to go ahead and switch over to removing. So this stuff from removing might seem really similar to what I said for add. First thing you do is you remove just like a normal BST using pointer reinforcement to do all your stuff. Then as you unroll the recursion, so while you're going back up the tree, just the same as adding, you update your height and balance factor and you check for rotations. The one additional note here is a lot of people tend to forget this. After you remove the predecessor or successor, you still need to do these updates. One second. So even though that's not like the main part of the remove, the predecessor and successor remove, which is probably a second helper method you had to write for this homework, or that you had to write for homework 4 and will have to use again for this homework, those are still going to involve a bunch of updates and potential rotations. Probably one of the more commonly missed things. So let's do an example with this tree, which is not quite the same tree we ended on last time, but we need to kind of set everything up to work differently. So let's remove 4. I'm going to make a note here that I'm going to use the predecessor, because it is a huge child remove. So first, let's take a look at what the rest of the tree looks like. So this part's all going to stay the same. I'm not even going to rewrite the heights and balance factors over here yet. Remember that we kind of have this nebulous pointer from pointer reinforcement. This node now has a 1 in it. And everything over here is currently unchanged. So we've done our removal of the predecessor. We've replaced the data in it. This is how you do the removal. This part's all been exactly the same as a normal BST. Now we update our height and balance factor. We determine that our height is 2, because this is 1, and we add 1 to that. Then we look at our balance factor. That's going to be -1 minus 1. So we determine that we have a balance factor of -2. And we say, okay, -2 balance factor, I have to do a rotation. So we look at the balance factor of our right child and see that it's positive, which means that we now have to do a double rotation because we've got this zigzag. And this is going to be a right-left rotation. That's how we're going to fix this tree. So the first thing we do is this right rotation down here, which is going to result in straightening this tree out. So we've got this 6 and then the 10. Everything over here is unchanged. We've kind of got these two floating pointers. We update the heights and balance factors over here. And then this 6 gets returned and set to the left child of 1. So that's our that's the first part of our double rotation, just like we did with the add method. Now we do the second part of the double rotation. That's the left rotation around 1. And that's going to result in us having 6, 10, which didn't change, then 1, everything over here stayed the same. We update the balance factor of 1, height and balance factor of 1. We update the height and balance factor of 6. And then we return 6 back up to get set to the left child of 20. Then we're going to update the height and balance factor of 20. It now has height 2 and balance factor 0. And now since we've updated the height and balance factor of the root and we didn't need to do a rotation, we're now done with our removal operation. So overall, adds and removals are really similar in terms of like their parallels from BSTs, that you basically just take your BST code and you're adding in all of these rotations and updates and balance factors to check. I'll give a little bit more on this, and then I'm going to talk a bit about some helper methods that you might find very useful to you to write on your homework that you wouldn't have had, or you might not have had most of them in your BST class. And then we'll talk a little bit about efficiency, and then that will be all of our content for today. Alright, doesn't seem like anything new. So let's go ahead and talk about some stuff that you might find useful to you on your homework. So while none of these are outright required things, we do recommend that you write a lot of helper methods on this homework. Obviously, you need helper methods for all of your recursive calls, but these are extra ones we strongly recommend you use in order to make your code a lot cleaner and more useful. The first is a method to update your height and balance factor. So this is just going to take in some node. You update your height and the balance factor just based on your children's heights and children's balance factor. So this method should not be recursive. You shouldn't be like calling it and then calling it on its, and then this method shouldn't like necessarily call it on its children or anything. This should be a really quick O of 1 calculation. Just fix my height, fix my balance factor. Simple as that. The next ones should be very obvious. You want a right rotation and a left rotation. That take in some node, they're going to perform the appropriate rotation, and you want them to do the appropriate updates. You remember earlier we talked about one of those last steps of the rotation was to update those two nodes that got changed in every single rotation, and then you want them to return that new root of the subtree. So these two methods should both return some node, which is the root of a subtree. This method doesn't have to, since it's just kind of updating something in place. So these ones should be really obvious. Basically everyone writes helper methods for these, but we have seen people that try to do it without them. Save yourself the hassle, write these helper methods. The next one is a non-intuitive one, and it's a method that we generally call something like balance. Now what balance is going to do is it takes in some node, it checks if that node is out of balance, and then if it finds that the node is out of balance, it's going to call the appropriate rotation methods. So what this might look like is it might have to do something like return left rotate node. It might have to do like node dot set left rotate node. Oh, sorry, this is not right. But the basic idea is this might have to do the double rotation. So this might have to do like you set your left equal to a left rotation on your left child, and then you would return a right rotate. I apologize, it's getting a little cramped, but this is just like a little bit of scribbling as examples. So this is going to do your rotations. So this balance method should also return a node, and it's most likely going to return a rotation call on the node that was passed in, possibly having to do a left rotation on or a right rotation on the child first if a double rotation is necessary. Now, a really common question is, why can't these methods be combined? Why can't I just have a method called update height and balance all at the same time? Well, very good question, and it actually will work most of the time. But an issue is that it's actually possible in the middle of a double rotation, after you've done the first rotation, when you try to update one of your node's heights and balance factors, you might actually find that you've created something else that was out of balance in the middle of your double rotation. If this happens and you're using one singular update height and balance factor and then balance method, then what will happen is in the middle of your double rotation, you'll try to add in an extra rotation randomly in the middle, and that is going to horribly break everything. So please separate these methods, and when you do the updates in your right and left rotate methods, you're just going to call the method that all it does is updates height and balance factors. Your rotations should not be able to create other rotations, if that makes sense. So separate these methods. Next one, relatively trivial node method we just like to call like get height or node height or something. All it does is it's going to return whatever height is stored in that node, or -1 if node is null. Now this seems really trivial because this is literally just a ternary statement. Why does it need its own method? The answer is because if you try to write that ternary statement, you'll find that you're writing that statement a lot. It's very often that you need the height of some node in some case. So writing this helper method just to avoid all of these null checks and avoid all of these null pointer exceptions is just a generally useful thing. This is probably the least required out of all of these. Definitely you should be writing these four. It would be very difficult to do without it. This one you can probably make do without, but it'll improve your quality of life just a little bit. Now, some notes that people will probably find helpful is assuming that you wrote your homework 4 code with pointer reinforcement. The biggest thing you'll be doing is you'll be copy pasting a lot of your code in, and all of these places where you had like return cur, instead of just returning that current node, you're going to, I should add, this should be update cur, and then return a balance of cur. So this will update its height and balance factors, and this will try to apply any appropriate rotations if necessary. So these changes are going to be like the vast majority of changing your BST code to changing your AVL code. Like for your add method, that's probably going to be it once you get those helper methods working, is just changing those two things. So definitely recommend writing these methods because it makes these changes really fast. Another thing is some people like to write helper methods to do double rotations. That is fine if you really want to do that, but realistically, a double rotation can just be accomplished by calling each of the two single rotations methods in turn appropriately, as I kind of explained in those other examples, like on that add sheet. I don't recommend trying to write some big method that like reassigns all the pointers all at the same time in a double rotation. If you're going to do a double rotation, implement it using two single rotations, calling these helper methods. It'll save you a lot of hassle. Another thing you might find helpful, I showed some pseudocode today, but there is some more pseudocode for these rotation things under the slides videos for the AVL slides. I don't know exactly which file it is off the top of my head, but you should be able to find it fairly quickly. But there's some more pseudocode, just a little bit more from what I talked about today. Now, next thing is going to be talking a bit about the efficiency and some common mistakes we see on the homework. That is going to be all the stuff today, so I'll give you a little bit more to ask questions or write things down for this, then we'll move on to that and end things off. Alright, we're getting some good questions, so I'll give it a little bit longer, just for these questions to get answered, or for people to finish typing their questions. All right. One second. All right. So next thing, or last thing, we're going to be talking about is efficiency. So BSTs, remember, had this degenerate case where you could have this really bad, like, diagonal linked list that would give you all these O of n efficiencies. But because AVLs always maintain this balanced property, we don't need to worry about any kind of worst case like that. So even in the worst case, it's not any different than the average case for an AVL. So these add, remove, search operations that we had average log n for a BST, for an AVL, that's going to be average and worst case log n. And we don't really talk about best case or anything, but it really wouldn't be any different than the average case. This is the important stuff. Probably the biggest change between a BST and an AVL, outside from just losing the whole worst case, is our height method. Remember that in a BST, we had to recursively calculate this in O of n time, but in an AVL, we can use our handy-dandy height variable that each node stores in order to do this in O of 1 time. Traversals, obviously, that's touching every single node in your tree. No matter what, that's always going to be O of n. You can't really get better than that. Otherwise, you're not really seeing everything. So, common mistakes we see on this homework. If your BST code was not working properly in homework 4, trying to copy and paste that into your homework 7 is not going to magically make it work. Look at your TA feedback from homework 4, make adjustments based on that before you start trying to use it in your homework 7. Likewise, if you wrote like look ahead BST code or didn't use pointer reinforcement, I recommend starting homework 7 from scratch. It's going to be a lot of work, but it's going to save you time in the long run. Yes, restarting it from scratch will save you time if you did not use pointer reinforcement for BSTs. We've seen it even like a couple days before the homework is due. We've recommended to people to restart their homework using pointer reinforcement because it would be a better way of solving their problem than trying to debug it without pointer reinforcement. That's how important it is for this homework. Remember that height is no longer a recursive calculation. You should be able to do all your height calculations in O of 1 time by looking at the variables of your two children, assuming that you need to update your current height, or in like just your normal height method, you don't even need to do any kind of update. Another thing, and I think even someone got tripped up on this earlier, remember that our balance factor is left height minus right height. We don't use the balance factors of our children, only their heights. Remember, in rotations, the order we update those heights and balance factors in is very important. We want to make sure we're updating the height and balance factor of that new child before we update the node above it. Otherwise, everything gets out of whack. So don't forget that. Now, in this is the exact note I said earlier. Make sure that you're not going to check for rotations in the middle of a double rotation. And if you separate your update height and balance factor and your balance methods like I recommended on the previous page, this is a non-issue for you. But if you're getting some really weird issues with double rotations, make sure that this isn't what's going on. Because we see that with a lot of people and it catches a lot of people off guard. So, I'll give you another minute or so to write stuff down, and then that will conclude the content section of today's recitation. With quite a bit of time remaining, we will get through our weekly card trick and then end things off with some time. Alright, it isn't really looking like we're having any big lingering questions, so thank you guys for learning some AVLs with me. Now, let's get into clearly the most boring part of all of these recitations, where I pretend like I'm good at doing skillful things, and you guys all pretend that everything's going well. So, this... I know I messed up last week's card trick a bit, but this one, I can tell you in advance, is most likely going to go poorly. I haven't really practiced this trick that much. I mostly started practicing it since yesterday, and I haven't really performed this trick all that much in general. So we'll see how it goes. Also, no, you're not colorblind. These are blue jacks. These, you see, we've got like blue cards instead of red cards. This is a really cool deck. I actually like it. But this is going to be less of a card trick and more of a story. This is going to be the story of how these 4 jacks are going to rob this bank. Now, this doesn't really look like much of a bank. It looks like just a bunch of cards, and that's because kind of it is. But in actuality, these cards represent a high-security bank, and these jacks are going to try to figure out exactly how they want to rob it. They're going to come up with their plan and get back to us later. So, we've got the jack number 1, jack number 2, jack number 3, and jack number 4. And these jacks are going to come up with their strategy, and then they will go ahead and rob this bank. So, bank is made up of 12 cards. We can go ahead and check. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 cards. So this comprises all of the what am I trying to say? This comprises all of our high security bank, these 12 cards. So this bank isn't just like one huge vault, it's actually a high security bank, so it's split into 4 different vaults of 3 cards each. So we can go ahead and separate that out now, get our first 3 cards, then our next 3, then our next 3, and finally our last 3. And that's going to be the cards making up our 4 vaults of this high security bank. Grabbing things from flat surfaces is hard. So, these 4 jacks have come up with a strategy. They're going to split up into each of these 4 vaults, try to grab as much cash as they can from them, and then go meet up somewhere through their secret escape tunnel and get out to freedom. So, first, jack number 1 is going to go inside vault number 1. Then jack number 2 is going to go inside vault number 2. Jack number 3 is going to go inside vault number 3. And finally, jack number 4 is going to go right on top of vault number 4. So, jack number 1 rummages around the bank, tries to take as much as he can. Jack number 2 is going to do the exact same. Jack number 3 is going to do the exact same. And last but not least, jack number 4 is going to do the exact same, except jack number 4 realizes that something's actually gone a little wrong here. You see, in vaults 1, 2, and 3, there were actually secret tunnels in these vaults, so that when the jacks tried to go in them, they actually all ended up trapped together in vault number 4, where they were promptly arrested and brought to justice. And that is the story of how the jacks tried and failed to rob a high-security bank. Thank you guys for coming to this week's recitation. I hope you guys enjoyed. You'll find the link to the tutorial for this on next week's announcement, in case you're curious and don't want to look it up yourself. Hope you guys have a wonderful rest of your week, and I will cut off this broadcast as soon as everything catches back up. See you guys.